So the next speaker is Brigitta Sipocz. I hope I pronounced that correctly. She's a DiRAC fellow at the University of Washington, and she's going to be talking about community software. Please go ahead.
Thank you, Aliu, for the introduction. I'm Brigitta Sipocz from the University of Washington. I'm an astronomer, but in reality, I'm working as a research software engineer, mostly focusing on open source community packages in Python. So I was asked to talk about collaborative software communities in my talk. And I would like to do that through a recipe that seems to be working very well, and it's the AstroPy ecosystem. So this is the one I know the best, and it also shares many of the common ingredients that other projects are doing, mostly in the Python, scientific Python ecosystem. So this is just a reminder, Python is the most popular language in astronomy at the moment. This popularity can be traced back to several reasons. One of it is that it's a free language. No one requires having a license, but most importantly, to the fact that in the mid-1990s, early 2000s, large efforts were put into developing common and shared scientific libraries that everyone can use and build up their tools. And the other reason is that Python is coming with an approach that is very open, and also platforms appeared like GitHub that made this sharing software so much easier. So one of the key ingredients is then open source. And here I would like to distinguish between different types of software on the internet. So putting a code on the internet doesn't mean it's open source. It needs licensing. But putting a software on the internet with a license doesn't mean it's a community software. It doesn't mean that it's open to the wider public, the wider community to come and bring their puppies, their features that then the community takes up and maintain. So there are these layering code on the internet, open source, and what we like to call open development. And one of the successes behind AstroPy is open development. So it started about 10 years ago. And before AstroPy became a thing, there has been several attempts, several packages and scripts and compilation that people wrote that are duplicating functionality. There were more than 20 implementation of coordinate transformation. So the whole project started to move all these resources into one central source and maintain only one and test that one and make sure that one is working. So AstroPy started as a community effort to develop a common core package for astronomy, and also to foster an ecosystem of packages. So the project itself is not the package, but it's a much wider ecosystem, and I will go into the details. And one key element here is that it's written by the community, for the community, by the community. So most of the developers are users as well, and all the users can become a contributor and a developer. So this ecosystem consists of 4 main parts. One of the biggest one and most well-known is the AstroPy package. It contains the core functionality that's shared and used by many parts of in astronomy. So it's very much topic independent. the very basic structures are put in this package. Coordinate transformation, infrastructure for modeling or handling of WCSs, unit conversions, and so on. A next up layer is the so-called coordinated packages. These are smaller packages, more specially focused, but they are still maintained by the same community. These are not single person, but the whole team behind it is the same. And we are also working on making these very much coordinated, so ensuring that they interoperating well with each other, they are compatible with each other. So this is one of the key elements in the ecosystem. And then there are infrastructure packages. So the team is also building a lot of infrastructure that are not astronomy specific, but are needed for all the astronomy packages we are building and distributing. So these are testing infrastructure, package templates. I will show a few examples. And also these infrastructure is available for the wider community to be used in their own more focused package software solutions. And we also have so-called affiliated packages. I will tell more about these. So these are people not necessarily in the core AstroPy team can propose their packages to be affiliated packages, and then they will go through a review process. So this whole ecosystem is somewhat but different in astronomy. So it's not yet necessarily true for other sciences, that things are so much well working together, but many other places are planning to build up a similar system. So I would highlight the coordinated and affiliated package approach that's very much unique here. And then what's in the core package, it's usually based on a community consensus. What can be added there? I mentioned these are very generic functionalities. One common requirement is that everything has to be tested, documented, and preferably be a stable code. We operate on a dual releasing approach. We have a long-term release that can be used for observatories and places where stability is utmost important. And we also, on top of that, we have more frequent feature releases. But in both of these release families, stability is one of the most important requirements. And the result of the open development model is that there is a growing number of users, and these users are turning into contributors. Also, as the number of users are growing, there is a growing number of issues on the issue tracker and growing number of feature requests. These, if they can be addressed steadily, that means that the package is more sustainable. It can be kept up, but there is a large seasonality in this handling of issues. Anyway, bottom line is there are a growing number of people getting involved. However, the committers per month is rather stable, around 20 and 30 people per month. It's not necessarily the same people, so people come and go, but there is a steady flow of stable maintainer group and contributor group. So I dig through my old slides, and this is what the AstroPy core package looked like 2 years ago. some numbers digged up from GitHub. So there were more than 10,000 repositories on GitHub that relied on AstroPi. Of these, around 1,000 were released on PyPI. And there are a few places on the internet that shows that how much effort they're working with estimations, how much effort went into a package. So based on these numbers, AstroPi also grew a lot. So I did the new numbers in the last few days. So contributors in the last 2 years grew around 30%. We have more maintainers. Just going back, and also GitHub switched on tracking and providing the numbers for us. So that changed a lot on the dependent repositories. And then, yes, as I mentioned, the release roadmap is having a steady cycle of releases, one in about every 6 months, but then also have the long-term support release that we are supporting with bug fixes for 2 years. So these are targeted towards observatories and places where operation is ongoing, so they can't opt into the latest and greatest versions. Big features are proposed by the community through a process called AstroPi Proposal for Enhancement. This builds on the idea that that is around everywhere in the Python ecosystem, that these proposal documents are submitted, then the community discusses it, and then a decision is made. And if it's accepted, then the development cycle starts. And for the releases, sometimes we like to set a focus topic. And in the last few have been either performance enhancement or adding new functionalities or major infrastructure refactorings. And then now about the team. So the team is a multi-layer team. So contribute multiple layers of types of contributions are in AstroPi, from the bug reports and feature requests. Those are contributions because user feedback is very important for us. Then many of these turn into pull requests by community members who hasn't been developing AstroPi before. So they become code contributors, and then eventually there is a road to become maintainer of modules or affiliated packages. So currently there are 28 people in maintainer roles and more than 400 individuals over the last 10 years contributing to AstroPi. And there are a multi-layer of named roles. They are detailed out in the team webpage. So what is driving this development is the open development that's driving this community building. So decisions are made out in the open, not in a seminar room in a department, but everything is happening out in the open, either on GitHub or in public community calls. Implementation details are on GitHub, and sometimes people like to say it's bureaucracy because most of the feature implementation is driven by the timeline of the individuals contributing and also the institutions who are willing to do the work. And all the collaboration are done remotely. So switching to remote collaboration due to the pandemic wasn't a big switch. We have been remote before. On the personal level, it's much more difficult, but on the team level, it's just as remote as it always have been. But of course, having face-to-face meetings are valuable, and we can have those this year. And then the AstroPi affiliated packages. These
these packages are going through review, where the reviewers are checking whether they following the coding, testing, and documentation guidelines, and that they are avoiding code duplication. So they use the existing AstroPy and affiliated package functionalities wherever it's possible and reasonable. And we provide the infrastructure help to the packages and to any astronomers. And so what type of affiliated packages exist? One typical group of packages where the functionality is under rapid development, they might be part of core later when they stabilize, but currently they need a different release cycle. Affiliated packages are quite often are having specialized functionality that are useful for a subtopic of astronomy. Good examples here is AstroML, which is a statistical and machine learning tool collection for astronomy, or PhotoUtils, that is the photometry package, or GammaPy, which is the package for gamma ray astronomers. And also there can be packages that are not compatible license-wise with the core package. And who uses AstroPy? We can only track that via citations, via user feedback. And sometimes we know from these feedbacks that it's used well beyond astronomy. In the National Park Service or at the Mapping Authority. And we also heard from other places that it's used in medical imaging or cancer research and so on. And then one crucial part of it is that it's set to have a very good infrastructure set up. And so what is this infrastructure? It's a very detailed developer guide of how to contribute to packages. So it's quite useful for newcomers. We have a large number of checks on pull request, extensive CI testing, documentation builds, and various bots. And one of the main part of this shared infrastructure is that there is a package template, which can be used as a cookie cutter for any scientists to set up their own packaging and distribution for their software. And it is aimed at as a starter package and with the ability to use the same setup and platform as other astronomers. So helping out and contributing will be much easier for others. And also troubleshooting will be much easier for everyone because the infrastructure is shared. So there are currently more than 400 packages are using this template or originally set up by this template, which is a huge success that we like to think that this made the life of so many astronomers easier.
Sorry, Brigitte, you have a couple of minutes.
Okay, thank you. And then any other example for community tools building is AstroQuery. So AstroQuery is started by some users who would like to have some Pythonic interface to access data archives. And it started with web scraping and reverse engineering of data telescope archives. But later it becomes so popular within users that the archives themselves joined the effort and joined the group. And now there are several of them who came on board and contribute and maintain their own modules. So it grew a lot. And currently there are over 80 contributors with 3 maintainers, and citations for the paper are growing. So the users and the user network is also growing a lot. And then I would wrap up with the last few slides with community building. So one of these is the so-called Open Astronomy. So this is an umbrella organization that oversees the internships that we are running and also workshops. This is running as an umbrella, so it includes not just AstroPy and astronomy, but also the solar physics ecosystem, Julia Astro, Polyastro, YT, so a much wider set of somewhat astronomy, astrophysics, and sky-related packages and ecosystems. So one way to grow this community consciously is running internships. So we are part of Google Summer of Code for quite a number of years. Roughly in Open Astronomy, there were 10 students this year. And we are also started participating in Outreach this year, which especially focuses on underrepresented people in tech. And in our case, it's in science. And the other way to grow this community is via collaborative meetings. The key to these meetings is that we are not direct competitors for each other, so the atmosphere is very collaborative. Examples is Python in Astronomy, Astro Hack Week, and various scientific software related meetings like SciPy or non-focus organized meetings. And some projects run their sprint events either in person, AstroPy does these, or dedicated online events. These are also very good to grow and to accrete new people. And of course, there are mailing lists and user forums. And then my last slides here is the summary. So what are the common things within collaborative software communities? First of all, I think an important point is there is no central institute that drives the development. It's the participants who are driving their own interest and pooling all these interests together. And also, it has to be open and handle community contributors. So people bringing their features, bringing their needs, and those feature requests will be addressed and integrated into the system. A very important point is to have a home platform that is accessible to everyone. And GitHub is very good with this. But of course, as everywhere, there are unique challenges. So to have a community software that's sustainable, it requires two very important points, which are not yet adequately addressed. One is the funding for these tools, funding for the community tools and for their maintenance. And then the other is career options for people who are doing the heavy lifting for these approaches. So in the US and especially in the UK, there is a movement called research software engineering. So many people are working towards building up career options for people who are mostly would like to focus on research software rather than traditional academic track. And then for further reading, I can wholeheartedly suggest this following book, which is Working in Public. Thank you very much.
Thanks a lot. Okay, so questions for Brigitta? So one question that is just natural is whether the activities that you are leading, Brigitta, somehow have a natural way to be incorporated into what Mario described for CIMA in the construction of this platform for MMA.
So yes, so some of the approaches are very much similar. So SEMA is also building, as far as I understand, a framework for sharing infrastructure. The AstroPy one is very much focused on Python and then on the non-cloud solution of distributing the software. But in SEMA, the driving factor is the science, one science topic, MMA. We don't really have that. So AstroPy is used from solar physics to cosmology to gamma ray astronomy. So it's much more generic. I suppose some of the things can be shared, of course, but some of the things that Mario needs is unique to them to handle streaming and alerts, and that's not present in our ecosystem. I'm not sure whether that answered the question.
Yep. Thank you. Anyone
I don't
else
have a question, but I just wanted to say I think it's a very inspiring project. I've been following it, and our particle physics institute called IRISEP, we definitely look to AstroPy as an example. So.
Yeah, I'm glad to hear.
Okay. Well, thank you very much, Brigitta. This is, again, very enlightening for the different projects that people are conducting.